Hey, welcome back. It's been a week and you've got more questions to deal with. Now, this first one starts with a very awesome idea in mathematics called the reciprocal, but we will get to a couple of ways of dealing with this. Division is really difficult. What that kind of looks like here is you've got 1, 2, 3, 4, 5, 6. And let's say that you colored in 5 of those because that's 5/6. Okay, so this is what we're looking at in this question. That's 5/6. And you're going to divide it by 10/9. And the method goes something like this. It comes from a reciprocal relationship, actually, that if I divide, so we should write this down, if I divide by a number, it's the same as multiplying by its reciprocal. So in that regard, we have to understand, I guess, what a reciprocal is. So let's go into a deep dive on reciprocals. A reciprocal is the number that you multiply a number by so that you get 1. Give an example. If you had 7, we're going to set up the scenario where you'd multiply it by something and it equals 1. Have a think for a second. What would that something be? Hopefully it didn't take you too long to realize that that something was 1/7. Okay, and 1/7 is the reciprocal of 7, as well as 7 being the reciprocal of 1/7, because if I had started with 1/7, then I would times it by 7 to get to 1. So a 7th and 7 are reciprocals of each other. It goes a little bit harder then, so let's try 3/8. What would you multiply 3/8 by to get to 1? Well, you probably guessed it. Essentially, you're going to have a fraction that turned the overall result into 1. So if the 8 was on top and the 3 was on the bottom, you would have a cross sort of cancellation to 1. And so the reciprocal of 3/8 is 8/3, leading to some really important rules. Firstly, the reciprocal of a whole number is 1 over that number. And the reciprocal of a fraction is the flip of that fraction. And where this whole thing works here is that if I flip 1/7, it would be 7/1. And 7/1 is just 7 because you're dividing it by 1. So that's how it works in terms of whole numbers and relating it to fractions, that all whole numbers can be written as divide by 1. So we've got this relationship where you just flip it upside down, and that's the reciprocal. Amazing, amazing relationship. It's really useful in division because if we divide by a number, it's the same as multiplying by its reciprocal. So this question here gets transformed in order to bring insight. Okay, so we're going to get used to that word transformation. It's not a magical word. It's not a word that you restrict to just those 4 types of transformations that you see in the GCSE maths book. In fact, transformations are a word used at the highest level of math to represent change. So 5/6 will remain the same because that's the thing we're dividing. Now, if we're dividing by 10/9, that's the same as multiplying by 9/10. And all of a sudden, it becomes a multiply question, which is far easier than the division conceptually. We've already gone through how to do multiply. And we said about just multiplying the denominators and the numerators, but that what we might want to do first is look at those as products of primes to see if any cancellation is going to occur. So we write all of the numbers as product of primes. 6 is 2 times 3, 10 is 2 times 5, and then we'll look to cancel. So we've got a 5, a 3, and that's it. What's left is a 3 on top, and on the bottom a 2 times 2, which is 4. So we've got 3/4 is the answer to 5/6 divided by 10/9. And who'd have guessed it? But there it is, and sometimes they are nice numbers like that. Okay, the next one is we're going to introduce some algebra. So level 4, not bad, it's getting a bit harder. It's the same idea as before, and then we'll look at cancellation. So we treat it as if it's a multiplication. So it's going to be that thing, which is 12x²/5, but instead of divide, we're going to multiply by its reciprocal. And so what we're going to do is put those into factors. 12 is 3 times 2 times 2, and we've got times x, and finally we're going to combine that 2 as well, so it's times 2. So there's a lot going on. Eventually, we will get rid of the stabilizers and do it without having to write it out, but until we understand fully, we don't want to change that. And another thing is, we're not here to rush. We're here to get it right. In an exam, you might get really flustered, and how are you going to stop yourself and readjust? You have to look back at structure, which is what we're doing here. Okay, so 5 times 3 times x. We can only cancel out if they're being multiplied. And as you can see, everything here is being multiplied. You see why I say that over and over? You've heard me say that before. I say it more than once because how are you going to remember it if you only hear it once? Sometimes it's not fair to think that's possible. Nothing else cancels. 2 times 2 times 2 is 8 and an x, and 5 is alone at the bottom. So there you go. Now, what's the fast way of dealing with this? Like, how would I do it? Well, this definitely is the first step to this algebraic fraction stuff. And if you were going to be quick about this, you would see, and there are shorthands, but you could say that the 12 divides by the 3, and that would leave a 4 on top. And the x squared will divide by the x to give just an x left on top, times 2. And then you'd have a 5, and then you'd tidy it up to be 8x over 5. So it isn't massively quicker, and you've got to be careful, but it's still possible to do it with less writing. You can imagine when the questions get really big and you'd have to do a lot there, right? Okay, new skill alert. We have to change an improper to a mixed and a mixed to an improper, okay? So we want to get an improper fraction, which means that the number on top is bigger than the number underneath. An example would be 9 over 5, okay? So you've got a bigger number on top. Interestingly, this means that the number is more than 1. So if I had 5 over 5, as we saw previously, that's equal to 1 because it's the same thing over itself. And then fractions that are less than 1, they are smaller on top. Okay, so this one is smaller than 1, and this one is bigger than 1. So that's what an improper fraction is. All right, improper is usually got different connotations, but it just means that it's bigger on top. So how do we do that? Well, one way is we see it visually. So I'm going to draw something visual here for you. Hopefully it's not too abysmal. As you can see, they're not equal, but you can imagine that they are for me. Thank you. And we're going to split these 6 in fifths. Okay, so that's 1, 2, 3, 4. Okay, that's the amount of holes that I've got there. I've got 6 holes. That's 1, 2, 3, 4, 5, 6. Okay, so each row, and I'll check out every other so you can see that it's rows. Plus I've got this little thing here. I don't know if you've ever been taught this or aware, but what's in between the 6 and the 2 fifths is actually an addition. And in this case, we just don't write that addition. It's quicker to say 6 and 2 fifths. So it's not just the holes here. We've got an extra 2 fifths off at the side. And so we've got to have another row of fifths, 1, 2, 3, 4, 5. And we're going to talk about how much we've got. So we have 6 holes, which is 1, 2, 3, 4, 5, 6, plus 2 of those fifths down there. Now, this is one way of looking at it like visually, and it's definitely not what I recommend going forward. But this visual is going to help us to understand why it's okay to do what we're about to do, because we're going to notice a pattern and then adapt to it. How many do we have coloured in? 1, 2, 3, 4, 5. Obviously, we've got 5 times 6 on the left here, which is 30 plus the 2. So we've got 32 fifths. Let me write that properly. F-I-F-T-H-S. 32 fifths. And in mathematics, we just write then that it's 32 over 5. 32 divided by 5, or 32 fraction bar 5. And this is an improper fraction because the top is bigger than the bottom, right? By quite a bit. So it's improper. So we found the answer just by writing it, but to be honest, that's a little bit tough. Look at how these numbers interact. How does the 6, 5, and the 2 turn into 32 and 5? Well, you can see that the 5 just stays the same because they're in fifths. That's pretty much all there is to that. But the question is, how do we get to 32 using 6, 5, and 2? We do the 6 times the 5. The clue here is how we worked it out when we added these up. You know, when we added this big thing, it was 6 across and 5, so 6 down and 5 across. And then we did 6 times 5, which was 30. So that gave us like the total parts there. So we times that together there. And then over here on the right, we had 2 extra. And where did we get that 2 from? It was this top number here. So we then add like that. So what does that look like in terms of a calculation? It'll be 6 times 5 and then plus 2. So we get our 32. And that's where our top number comes from. Right, so we used that color already. Our top number comes from the multiplication of the quotient with the divisor and then adding the remainder. Okay, so there we get 32 over 5. And hopefully we can see that again in action down the bottom. Convert to an improper fraction. So now it should be as quick as just doing this, multiply, and then add together. Now, you're welcome to draw it out every single time, but let's just try and speed up here. We've got 2 times 8, and then plus 7, which is 16 plus 7, which is 23. And then it's going to be all over the same denominator, or you could call it divisor. Okay, so we've got 23 over 8. Awesome. Now we've got to know how to add fractions. Okay, so all of this is going to be useful later on because algebra requires knowledge of fractions. With 3/4 and 5/6, you can see that this is in quarters and this is in sixths. That's no good. Okay, you can't add apples and oranges and expect to have a certain amount of apples. They are always going to be separate because they're different things. And so with the fourths, the quarters, and the sixths, we have to try and get them into a way that we can work with them so that they are the same. And beautifully, we looked at this earlier with the equivalent fractions. Okay, so when we're cancelling fractions down, you can do the same. So let's take 1 over 3, for example. We can multiply the top and the bottom by 2. And why is that? Because if we multiply by 2 over 2, you're essentially just multiplying by 1. And that's beautiful because that means it doesn't change the number at all. So if I multiply by 2 over 2, I write this. It's the same as 1 over 3. It's absolutely the same, done nothing to it. But what we've done is found an equivalent format so that we can then work with it and gain insight. So timesing it by 2 over 2 then transforms it to 2 over 6, which is an equivalent fraction. But 1, instead of having a denominator of 3, is now 6. So maybe having 6 on the bottom is better, and in our case, it definitely is. We're trying to find one where they can both be the same. Now, it's not so easy in this question. You can't just multiply by one thing. It's not going to be that easy. We have to think about what we could times 6 by and 4 by to get to the same. Now, this is called finding a common denominator. Common means it's in common. Best way of looking at it is the 4 times table for some inspiration. So 4, 8, 12, 16, 20, 24, and then the 6 times table. And I can see maybe the quickest time where they're going to have something equivalent is 12. Let's aim to get 12 on the bottom so that we can add them together. You cannot add fractions together without the same denominator, okay? That's just how it's going to work. Remember that rule, it's important. So how do we get 6 to be 12? We have to times it by 2. But remember, you can't just times a fraction by 2 on the bottom because it will change it. You can only do it if you do the same to the top. Okay, so at this point, because that's a lot of working out, it's easier to just write times 2 as your little plan. That would therefore make the right-hand side 10. Now, how would I get 4 to 12 on the left fraction? We focus on this fraction now. You would have to multiply this one by 3. And remember, do the same to the top. That would make it 9 over 12. And therefore, in total, we can now add, because they're the same. This is a certain number of twelfths. This is a certain number of twelfths. And so they add together real nice. So we've got 19 over 12. Now, what type of fraction is this? I can hear you say it right now. It's an improper fraction, isn't it? So if you want to give it as an answer, maybe I'll put that there. If you want to give it an answer like that's a little bit nicer, you do a mixed number. But check this out. 19 over 12, how big is that? Is it more than 1, less than 1? It's actually kind of hard to tell, isn't it? Especially if you had a number like 373 over 19. How big is that? You cannot say quite quickly. Maybe you can say because you know that 12 times 2 is 24, and so it must be just less than 2. But let's just say it's pretty difficult to see at that point. So what we're going to do is change it to a mixed number, which is going backwards from the previous question. This is our new skill for us. So how do we go backwards? 19 twelfths is where we have, let's say we split something into twelfths, which is a 3 by 4, like so. And then we have that twice. We've got a whole of that, which is 12 twelfths, 13 twelfths, 14, 15, 16, 17, 18, 19 twelfths. That's what 19 twelfths look like. It's like 1 and maybe more than a half, right? So we could say it goes in once, which is our whole 1, plus 1, 2, 3, 4, 5, 6, 7 of those twelfths over there on the right. How do we get these numbers from 19 and 12? Well, you can see hopefully that 19 take away 12 is 7. And so that's where the numbers come from. We know that 12 goes into 19 once, and the remainder is 7 over 12. Okay, so we write it like that to show the quantities, right? And if you did it like this way with a diagram, then you know that the add doesn't need to be there. You could just write it close. Awesome. Subtract. So we can't subtract these unless they've got the same denominator. So what we'll often find, rather than messing around with the 12 times table and the 18 times table, is that sometimes it's easier to just do 12 times 18. Now, if you do 12 times 18, it means that they are both factors of the product, which is the 12 times 18. Okay, so that's 180 plus 36, that's 216. So you can see that the 12 and 18 are factors of this product. And so if you did use 216, you know that they both go into it. That's a real bonus. The downside is that 216 is quite a large number. But nevertheless, we'll have a look at that, and it might make our life easier. So 12 times 18 will give us 216. Do the same on the top. And it's 18 times 12 will give us 216, so we'll do the same on the top. Our new question is 18 times 11. We'll do 10 times. It's 180 plus 18. That's 198. Over 18 times 12, so that's 180 plus 36, which we know is 216. 7 times 12, which is 84, and we know that we're aiming for 216 already. Okay, so let's move that to the side and complete this, because we now have a common denominator, which means we can focus on this number of 216ths, take away this number of 216ths. And so the difference between the two is 114. Just double check that. We've got 498, yeah. So 114 out of that same denominator. Now this is where we can do factors that will help us. This time I'm not going to go for prime factors. I'm just going to show you what might be a cool way is to do it, because we know they're both even, to do it slowly. So if we halve 114, we've got 57. Is that a prime number? I think it is. And then we've got 2 times 108. Okay, it's not a prime number actually, no, it's not. So that 2 will definitely cancel. And now our number is a little bit nicer. I can see that 57, a 3 goes into it, and it would be like, 30, 60. So it would be 20, but take away 1 means it's 19. So I'm going to divide it by 3. So that would be 3 times 19. And then divide that bottom by 3, which I just got an inkling it will divide by 3. So we've got 30, 60, 90, plus 18. So that's 36. So 3 times 36. All right, so this is looking good because a prime number has appeared on the top. I think, therefore, we have to stop because we're not going to find any more factors, and we've fully cancelled that down. Okay, now we're going to mix this up a bit. We're going to have to find we have to do it in order. So here's the next new rule. BIDMAS has to be done in order. So with that in mind, we're going to do brackets first. We have to have a common denominator. I can see that 3 times 4 is 12. So I'm going to work towards that one. And that times 3 on the right. So I get 12. And that, if you're wondering, stays the same because that's not what we're changing here. We're just changing the fractions. And that's 3. And that's still a result, like it's separate to divide by 5 over 6. But what we can do is say, instead of divide by 5 over 6, we know that eventually that's going to be timesing by its reciprocal, which is going to be easier than the division. Last step before the final is that we are going to combine these two together because we now have a common denominator. That's going to give us 8/12 plus 3/12, which is 11/12 multiplied by 6 over 5. And that's 66 over 60. Now you could, at this point, start doing non-prime again and see there's a lot of 6's going on there. So it probably does divide by 6. So that would be 6 times 11 divided by 6 times 10. Do you think I am extra for doing that? Yeah, but you're saying yes. I'm not extra for writing this. You know why? Because if I ever get into the habit of thinking that they just cancel and it's magic, I'm never going to... Well, I'm not never, but it's going to be harder for me to adapt to algebra because I won't realize that a factor is needed in order to cancel, okay? So 11 over 10, which if you want to change to a mixed number, is 1, remainder 1 over 10. All right, let's keep going. Same thing now with algebra, all right? So with algebra, we have to find a common denominator just like usual, but you don't always have to change both. In this case, the 3 could multiply by 4 in order to get to 12, right? And so just stick to that. Now, the threat, I suppose, is it's the whole thing that's multiplied by 4. And so, therefore, we are going to change. We get 9x over 12. There's nothing wrong with that one. Keep it the same. But the second one becomes 4 times 2x. Now with this, we've got 4 times 2 times x. So we can have that as 4 times 2, we can see as 8x, all over 4 times 3, which is 12. Now we have the magical common denominator, and we're going to do 9x take away 8x. Wow, here's a new thing. This is dealing with algebraic expressions. So 9x's take away 8x's. You can say that an x is like an x because it's the same letter. What does that look like? It's 9 take away 8. Okay, each of these little dots are x. So you've got 9 of them, take away 8 of them. You've got, how many x's do you have? You've got 1x, haven't you, right? So you don't write 1x, you can just write x on its own, but you can write 1 over x. You can write 1x, I suppose. And you keep the same denominator, so it's out of 12. Now, it doesn't look like an answer that you're used to seeing because it's got an algebraic term in it. And there's nothing wrong with that. All I can say is get used to seeing answers that are not numbers, because that's exactly as it is. As soon as you know what x is, you can figure out the number. All right, now we're moving on to solving. Okay, so this is a solving where we've got to deal with fractions. Okay, so don't worry about the 3/10 just now. We are going to work on what solving means. Now, if it says solve for x, it means get x alone. You've got to isolate x. Now, the typical way of solving equations is if we start with, let's say, x plus 1 equals 2, we might draw a diagram and say there's x, which we don't know, plus a 1, we'll call it a dot, and that equals 2. And because they're equal, we could imagine it in many different ways. One of the most well-used ways is to imagine that it was a balanced scale. And that this balance scale has to adapt. And if you took away something from both sides, like one of the dots, it would remain balanced because it's still got the same on each side. But that's essentially what we're going to do here. We're going to use the balance method, and we're going to take away the same thing from both sides until we have this scenario here. This scenario says that our box, which is x, equals 1. So if we can get x alone, that's why our aim is to do that. If we can get x alone, we can say what it's equal to. Right? So the aim of solving is to get x alone. We'll keep that there now. Now, to get x alone, we've got to kind of do the opposite things to get it on its own. Now, previously we saw that little 1, we could just take it away from both sides. Here, it's being divided by 5, so we have to do the opposite of that to get rid of that. So if you're dividing it by 5, you're making it 5 times lighter. If you make it 5 times heavier, that will cancel out that effect, but you have to make the other side 5 times heavier as well. So my method is to get rid of a divide by 5, we're going to times by 5. That's why earlier I said you need to know your opposite operations. This fraction bar here, it means divide. Okay, so the opposite of divide is times. And then we're going to look at our knowledge of fractions. So if we have 3 over 10, and we're going to times it by 5, another new skill is coming in. Whole numbers have to multiply the numerators of fractions. Okay, so that numerator is 5. Therefore, we're going to have 3 times 5 all over 10. Now, I can prove this is true because remember earlier when we said that 5 can be written as 5 over 1. Now you see it. The 1 and the 10 will multiply, and the 3 and the 5 will multiply, but the bottom, that's nothing going to happen to that. It's just going to stay 10 because anything times 1 is the same. So really, when you see a number, you ought to be thinking it's going to multiply the numerator only. And so then that becomes 15 over 10. Okay, so we've worked on that as we go through. So what I feel like we should do is give this a little bit more space so we can see. And put that in line there like that. So if we do that, we're going to have x equals 15 over 10. So that's the methodology. We're going to do the same thing to both sides and then see the fallout with the aim that we're trying to get x on its own. Now, we can see x equals 15 over 10 could do with some cancelling. And we're going to say 3 times 5 all over 2 times 5, right? And then the 5's cancel to be 3 over 2. Now, you may think it's tedious, but as I said, if we keep doing it this way, we're going to get a feel for it. When we get to the algebra side, we're not going to be scared because it's the same method. It's not anything new. Okay, lastly, to express this as a decimal, lovely skill. So this little thing here in the middle is called a fraction bar. And it means, do you know what it means? What operation? Take away? Nope. Division. So this is essentially just 7 divided by 20. Now, I did ask that the prerequisite for this course is that you know how to do your basic multiplication, the division, all that sort of stuff. And so I'm not going to go through it more than once, but here is how you do it by hand. You do a bus stop method. So we're going to say 7, which is like essentially that, and we're going to divide it by 20. So how many times does it go into 7? It doesn't. So we carry that over, and that's 3, remainder 10, and then that's 5. Okay, and there's no remainder anymore. So we know that 7 divided by 20 is 0.35. Now, obviously, another prerequisite is a calculator. You can do that division on a calculator, 7 divided by 20, and it will give you 0.35. Although, to be fair, it might give you a fraction, like 35 over 100 or something. And you would just then go to your menu and change it to a decimal. Okay, so that's it for this week. Those are those questions. It's good to see them in action, and gosh, we got through a few, eh? But it's important to see how they break down so that if you ever see them again, you know that you've got a coping mechanism, and you're not just going to blindly trust it. It's not just a bunch of tricks that feel like they're random. There's a reason behind it all. And again, if you've got any other questions, put them in the comments below, and I'm going to address them. I'm here for you. And how about we get the whole world feeling confident with algebra? See you in the next one.